The IEEE Std.519-1992 is found within the Green Book, officially named IEEE Recommended Practices and Requirements for Harmonic Control in Electric Power Systems. This standard serves as a guide for the design, installation, and operation of static power converters, aiming to minimize harmonic distortion in electrical power systems. The Green Book is highly regarded as a leading reference for harmonic studies applied to power systems. IEEE Std.519-1992 specifically focuses on providing guidance for harmonic control and reactive compensation related to static power converters. The standard addresses several key areas. Firstly, harmonic distortion limits, which define the acceptable levels of harmonic voltage and current within the power system. Secondly, harmonic measurements, outlining the methodologies and instrumentation used to accurately assess harmonic content. Thirdly, harmonic mitigation techniques, detailing strategies and technologies for reducing harmonic distortion. Finally, reactive power compensation, discussing methods for managing reactive power to improve power quality and system performance. Harmonic distortion is a phenomenon in electrical power systems caused by nonlinear loads drawing current in a non-sinusoidal manner. These non-sinusoidal currents introduce harmonic frequencies into the system, which are integer multiples of the fundamental frequency, typically 50 Hz or 60 Hz. Excessive harmonic distortion can lead to several detrimental effects. Firstly, increased losses in electrical equipment such as transformers and motors, due to the high frequencies causing increased eddy current and hysteresis losses. Secondly, overheating of conductors and equipment, potentially leading to insulation breakdown and premature failure. Thirdly, malfunction of sensitive electronic equipment, as harmonics can interfere with their operation. Fourthly, inaccurate readings from metering devices, leading to billing discrepancies. Finally, resonance conditions, where the interaction between harmonic frequencies and system inductance and capacitance can amplify harmonic currents and voltages, causing severe overvoltages and equipment damage. IEEE Std.519 provides a framework for limiting harmonic distortion to acceptable levels, ensuring the reliable and efficient operation of electrical power systems. The standard defines total harmonic distortion, abbreviated THD, limits for both voltage and current. THD is a measure of the effective value of the harmonic components of a waveform relative to the fundamental component. Voltage THD is typically limited to 5% at the point of common coupling, which is the point where a customer connects to the utility grid. Current THD limits vary depending on the size of the customer's load relative to the size of the power system. Smaller loads are allowed to inject higher levels of harmonic current than larger loads. The standard also addresses individual harmonic components, limiting their magnitudes to prevent specific problems such as resonance. Accurate harmonic measurements are crucial for identifying and quantifying harmonic distortion in power systems. IEEE Std.519 specifies the requirements for harmonic measurement equipment, including accuracy, bandwidth, and resolution. Harmonic analyzers are commonly used to measure harmonic voltage and current. These instruments use digital signal processing techniques to decompose the waveform into its individual frequency components. Current transformers and potential transformers are used to isolate the measurement equipment from the high voltages and currents in the power system. Measurement should be taken at the point of common coupling to assess the harmonic impact of a customer's load in the utility grid. Measurements may also be taken at other locations within the power system to identify the sources of harmonic distortion. Several techniques can mitigate harmonic distortion. Firstly, harmonic filters, which are tuned circuits designed to block specific harmonic frequencies. Secondly, passive filters, which consist of inductors, capacitors, and resistors, are relatively simple and inexpensive but can be bulky and difficult to tune precisely. Thirdly, active filters, which use power electronic converters to inject harmonic currents that cancel out the harmonic currents produced by the load, are more complex and expensive but offer better performance and flexibility. Fourthly, multi-pulse converters, which use multiple rectifier circuits to reduce harmonic distortion, are commonly used in high-power applications. Finally, harmonic reducing transformers, which are designed to minimize harmonic currents, can be used to supply sensitive loads. Reactive power compensation is another important aspect of power quality. Reactive power is the power that oscillates between the source and the load without doing any useful work. Excessive reactive power can lead to voltage drops, increased losses, and reduced system capacity. Static power converters, such as variable frequency drives and high voltage direct current transmission systems, often generate or absorb significant amounts of reactive power. IEEE Std.519 provides guidance on compensating for reactive power to improve power quality and system performance. Several methods can compensate for reactive power. Firstly, capacitors, which supply reactive power to offset the reactive power consumed by inductive loads. Secondly, reactors, which absorb reactive power to offset the reactive power supplied by capacitive loads. Thirdly, static var compensators, abbreviated SVC, which are power electronic devices that can dynamically adjust the amount of reactive power injected into the system. Fourthly, synchronous condensers, which are rotating machines that can supply or absorb reactive power. Choosing the appropriate reactive power compensation method depends on the specific application and system requirements. The Green Book provides detailed information on the design, installation, and operation of these compensation methods. IEEE Std.519 is a valuable resource for engineers, technicians, and facility managers responsible for maintaining power quality in electrical power systems. By following the guidelines in this standard, users can minimize harmonic distortion, improve power factor, and ensure the reliable and efficient operation of their equipment. The standard is regularly updated to reflect the latest technological advancements and best practices. Consulting the latest edition of IEEE Std.519 and the Green Book is essential for staying current with harmonic control and reactive power compensation techniques. Applying IEEE Std.519 involves a systematic approach. Firstly, identifying harmonic sources within the power system by conducting a harmonic survey to measure harmonic voltage and current levels at various points. This helps pinpoint the equipment or processes contributing the most to harmonic distortion. Secondly, evaluating the impact of harmonics in the power system by comparing measured harmonic levels with the limits specified in IEEE Std.519. If harmonic levels exceed the limits, mitigation measures are necessary. Thirdly, selecting appropriate harmonic mitigation techniques based on the characteristics of the harmonic sources and the specific requirements of the power system. This may involve using harmonic filters, multi-pulse converters, or other techniques. Fourthly, designing and installing harmonic mitigation equipment by carefully considering the filter's tuning frequency, impedance, and power rating to ensure it effectively reduces harmonic distortion without causing resonance or other problems. Fifthly, verifying the effectiveness of harmonic mitigation measures by conducting post-installation harmonic measurements to confirm that harmonic levels are within acceptable limits. Continuous monitoring of harmonic levels is recommended to detect any changes in harmonic distortion and ensure the mitigation equipment continues to function properly. In addition to harmonic distortion limits, IEEE Std.519 also addresses voltage notching, which is a type of voltage distortion caused by the commutation of power electronic devices. Voltage notches are characterized by sudden dips in the voltage waveform, which can disrupt the operation of sensitive equipment. The standard provides guidelines for limiting voltage notching to acceptable levels. Mitigating voltage notching typically involves using line reactors or other impedance increasing devices to reduce the rate of change of current during commutation. Power factor correction is closely related to harmonic control and reactive power compensation. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the current is reactive, which increases losses and reduces system capacity. IEEE Std.519 encourages users to maintain a high power factor to improve system efficiency and reduce utility costs. Power factor correction can be achieved by adding capacitors to the power system to offset the reactive power consumed by inductive loads. Automatic power factor correction equipment can automatically adjust the amount of capacitance to maintain a desired power factor. Implementing IEEE Std.519 requires collaboration between utilities, customers, and equipment manufacturers. Utilities are responsible for maintaining voltage (THD) within acceptable limits at the point of common coupling. Customers are responsible for limiting the harmonic current injected into the utility grid. Equipment manufacturers are responsible for designing equipment that minimizes harmonic generation. By working together, these stakeholders can ensure that electrical power systems operate reliably and efficiently. Understanding the terminology used in IEEE Std.519 is essential for proper application of the standard. Firstly, point of common coupling, abbreviated PCC, which is the point where a customer's electrical system connects to the utility grid. Secondly, total harmonic distortion, abbreviated THD, which is a measure of the effective value of the harmonic components of a waveform relative to the fundamental component. Thirdly, total demand distortion, abbreviated TDD, which is a measure of the harmonic current injected into the utility grid relative to the customer's maximum demand current. Fourthly, individual harmonic distortion, which is the magnitude of a specific harmonic component of a waveform. Fifthly, harmonic filter, which is a tuned circuit designed to block specific harmonic frequencies. Sixthly, reactive power, which is the power that oscillates between the source and the load without doing any useful work. Seventhly, power factor, which is a measure of how effectively electrical power is being used. Finally, voltage notching, which is a type of voltage distortion caused by the commutation of power electronic devices. The Green Book provides detailed definitions of these and other terms related to harmonic control and reactive power compensation. The IEEE Std.519-1992 and subsequent revisions provide a comprehensive framework for harmonic management in electrical power systems. It is essential to stay current with the latest edition of the standard and to consult with qualified professionals when implementing harmonic mitigation measures. By following the guidelines in IEEE Std.519, users can ensure the reliable and efficient operation of their electrical systems.